Okay, so now we will discuss about an alternative approach, and this code will be provided to you. Okay, so this method is called the adaptive integration. Okay? So you will write the code for the trapezoidal rule, and the adaptive integration code will be provided to you. Okay? So in case of adaptive integration, let's move on to the part for adaptive integration. Why does uh, says adaptive? Term adaptive actually means that we are not fixing any value, rather we will set the value depending upon the situation. Okay, adaptive means something that can adapt with the environment, right, or adapt with the situation. So in case of trapezoidal rule, we had to set a fixed value of h, but in case of adaptive integration, we will not set the fixed value of h, rather we will set the value of h depending upon our interval, the given interval. Okay, uh, let's assume we have been given an interval that's, so the x interval is, so first of all I should write the adaptive integration means the h is adaptive. Okay, adaptive means not any fixed value, rather value will be determined depending upon the interval. Okay, so that's why we are calling it adaptive. So it can change its value depending upon the situation. Okay, so let's assume we have been given the interval in this manner. So this is, let's say, our starting point x1, and this is, let's say, our ending point x2. So this is our given interval where we have to determine the integration or determine the area under the curve. Okay, so in this case we will start in this manner. How we are going to start? We will first divide this interval in two equal parts. Okay, so we will determine its midpoint and define h. So this point will be x1 plus h. So it would be our h, and it would be our h. Okay. So in this case, the h is very large, right? So our we will have a large error. Then what we are going to do, we will repeat this thing, like copying this line. So in this case, we will have a large error. Then what we will do, we have calculated already the midpoint here, right? This midpoint. We will divide this portion once again. So we will get the new points here. These portion will be equally divided into two parts. This left portion will be equally divided into two parts, and this portion will also be equally divided into two parts. So here would be our new point, and here would be our new point. And then we will define h as this. It would be our h, and similarly it would be our h. So in the first case, we actually considered only two segments. For the first case, we actually considered only two segments or two trapeziums or two segments, if I say. But for the second case, we are considering four trapeziums, or we are dividing it so many times. But as h is large now, we may consider h is large, we can divide it once more, right? That's the way we will follow in case of adaptive integration. So we will divide it once more. Each of the segments will be divided into two parts. So h will get divided once again. Okay, so and we will do this thing and calculate the areas and compare in between them. So we will calculate the areas here. We will calculate the area for the first one, then we will calculate the area for the second one, and then we will calculate the area for the third one, and similarly we will divide it once again. So our midpoints will now come here. So h is divided once again. It will be our new h. And we will calculate the area once again. Therefore, and what we will do, we will calculate the difference. Okay, calculate the difference in between the two areas. Like we will calculate the difference in between area 2 and area 1, and if the difference is a large value, then we will consider the error is large, and then so we will do this thing. We will calculate a2 minus a1. Okay, it will be our error, and we will take its absolute value. So it would be our error for the first case, and similarly we will calculate the error once again. Let's mark the errors in separate color. Similarly, for the second case, the error will be a3 minus a2. For this case, the error would be a4 minus a3. So for the first cases, the error would be a large value, but as we are dividing the value of h more and more, the error would become less. Okay, the error would become less, and we will set a threshold value, or we will set a tolerance value, how much error we are going to tolerate. Okay, so we will calculate the error continuously and check with the tolerance value. So we will set a tolerance value and calculate the error with the tolerance. If the error is greater than tolerance, we will continue doing this thing. Okay, so if the error is greater than tolerance, it means the error, we don't want the error to be this large. Okay, we are not going to tolerate it. So what we are going to do, we will continue to do this thing. It means we will once again divide it into two parts, or we will make the value of h smaller once again, and we will continue to do this thing. So we will get h here, h here. So h would be pretty small now. H would be pretty small here. And in one step, we will see that the error is less than the tolerance value. So if the error is less than the tolerance value, then we are satisfied. Like we will tolerate, or we will allow this situation. Okay, tolerance means how much we are going to tolerate, আমরা কতটুকু সহ্য করব, or how much we are going to allow. If the error is greater than tolerance, then we are not satisfied. Actually, we are not going to tolerate it, we are not going to allow it. But whenever the error is less than the tolerance value, then we are satisfied, like yes, we can stop now. Okay, so uh, until fulfilling this condition, we will continue to do this thing. We will calculate the areas continuously and calculate the errors as well. Okay, this error will be a5 minus a4. And when the error is less than the tolerance, then we can consider this area as our result. Okay, whenever we have found that the error is less than the tolerance, it means the error is much less, we are satisfied now, then the last calculated area will be our final result. So these area 5 will be the result of the integration, be our integration result. Okay, so the idea is pretty much similar to trapezoidal rule. The difference is that the h value is adaptive now. We are not going to set any fixed value for h. Okay, we are not going to set any fixed value for h, rather we will continuously change the value of h and see when our error is less than the tolerance value. If the error is less than tolerance, then we are satisfied with that h value. Okay, the main motivation of adaptive integration is that we cannot set the h to a very low value. If we set the h to a very low value, then there might be some issues. As I mentioned, lower h gives us better result, but how low or how small? Here comes the question, right? Smaller h gives us better results, but how small? So how small? The adaptive integration gives that answer. That whenever this error is less than the tolerance, then we will accept it as our integration value. Okay, so is the idea clear to you?
Yes, sir.
Okay,
But can
yeah,
you explain like what is tolerance value?
okay, the tolerance value will be set by us. Like we can set the tolerance value
Okay.
to a very small one. Like we can set the tolerance to 10 to the power minus 5 or a very small number.
Okay.
It would be set, or it would be defined by ourselves,
It would be given in the question, right?
given in the questions, or you can consider it to a very small value, like 10 to the power minus 4 minus 5, very small value.
Okay.
Okay, so now we will go for the MATLAB code for adaptive integration. Let me share my whole screen. Okay, so this is the code for the adaptive integration. Okay, so what we are doing here, in case of the adaptive integration function, this function will be provided to you. Okay, so no worries. This value will be the value of the integral, or the value we are going to calculate for determining the integration. It would be our output variable. So this value will be returned. The function name is the adaptive integration. You can name it anything you wish. Then we have to send the function, like we have to use the inline function method that we saw earlier. Okay, so we have to send this function. Then x1 is our lower limit, x2 is our upper limit, and this e is our uh, tolerance value. Okay, this e is our tolerance value, how much error we are going to tolerate. Okay, so we are writing format long. Format long actually refers that we are going to consider more decimal places. Whenever you write format long in your code in this way, then MATLAB will consider more decimal places. Okay, MATLAB will consider more decimal places like this, like a very long string of decimal places, right? So whenever you write format long, you will get more decimal places in the code. So we are starting with the same way, like h is equals x2 minus x1 by 2. We are calculating the value of h, and in the first step we actually calculated h by dividing it into two equal segments, right? H was calculated by separating it or dividing it into two equal segments, right? X2 minus x1 divided by h, sorry, divided by 2 into two equal segments. So h is calculated in this way, x2 minus x1 divided by 2, and then we are calculating the integral. Okay, so if you look carefully, this is actually the implementation of the trapezoidal rule. This is actually the trapezoidal rule. The initial point, the function value of the initial point, the function value of the last point, it was get divided by 2, and then we have to sum all the other y values like this. The function value or y value for the first point, the function value for the end point, and the function value for the other points. They are divided by 2, and we will sum all of this. So it has been implemented by this line, like f of x1 plus h, and we are incrementing by h, and our last point is x2 minus h, right? Because if we look carefully in case of trapezoidal rule, uh, this second point was x1 plus h, and we are incrementing by h, and this last point will be x2 minus h, right? This last point will be x2 minus h. So we are actually implementing the trapezoidal rules code here. The first function value, the second function value, they are getting divided by 2, and the other function values are getting added, and all of this thing is multiplied by h. As we can see, all of these things should be multiplied by h. Okay, so in case of adaptive integration, we have calculated the h value, and then we are implementing the trapezoidal rule, and then we are just dividing h by 2. As we saw in case of adaptive integration, the h gets divided by 2 each time, right? Here h was this long, now h is this long, so h has been divided by 2, and again h will be divided by 2, and we will go on. So h is divided by 2, and the second area is second area, or the second integral, if I want to say, the second integral is calculated with this new h value. All of these things are saying just our h value is changed. So as I mentioned, now we are going to calculate the error. The error would be the difference in between these two areas. So the difference in between these two integrals. So for determining the error, we are defining an empty array of e, and for storing the value of h, we are defining another empty array, that's h. Writing like this means we are defining an empty array, right? So an array that has no element in it initially. So we are calculating the error, the I2 minus I1. If we subtract I1 from I2 minus I1, then we are taking its absolute value. And as long as this error is greater than our tolerance value. So if error is greater than tolerance value, we have set this value initially from the main function. So as long as this error is greater than the tolerance value, so error is greater, so we will continue doing this thing. If error is greater than tolerance value, we will continue doing this thing over and over again, as long as uh, the error becomes less than the tolerance. Okay, so we are repeating this thing over and over again. As long as the error is greater than the tolerance, we are inside this while loop, and we are saving the error in this E array. The previous array is concatenated. Okay, the previous array was the empty one, and with the empty array, this new error value is stored. Okay, and similarly for the H array that was empty earlier, with this empty array, the new H value, this H value has been stored, and it will be concatenated within this loop. So this array will be the length of this array will increased continuously. Okay, new values will be concatenated in this position. Concatenated, or I can say it as new values will be get in the new positions of this array, the right positions of this array. Okay, and we are considering calculating the new integral, dividing h once again. So we are dividing h once again and calculating the new integral, then looping inside this whole loop as long as the error does not get less than our tolerance value. Okay, so whenever the error becomes less, then we will break in this while loop. The condition will not be satisfied, so we will break from this while loop, and our final value would be the last calculated integral result. Okay, the final value would be the last calculated integral result, and we can plot these to determine how h has been changed or how the error has been changed to get an observation. Okay, so the key thing is we are actually uh, dividing h by 2 continuously and calculating the area by trapezoidal rule, and we are doing this thing over and over again as long as the error is greater than the tolerance. Whenever the error becomes less than the tolerance, we just stop there. So we will break through this loop, and our value would be this I2, the last integral value, and this value will be returned to our main function. Okay, so if I keep the script function and run the code. So in the main script, we are willing to calculate the cost function. Okay, so we are defining our function using the inline function, and the function is the cost function. You can mention the parameter as well by putting a comma, or you can neglect it. Okay, so whenever you are defining a function, you can also mention the variable by putting a comma, or you can neglect it as well if you wish. So we are actually integrating the cost function here, cosine function. The error limit has been set as 10 to the power minus 4. 1e minus 4 is referred to 10 to the power minus 4 in MATLAB. Okay, so here is our upper limit, Here is the lower limit 0, and here is the upper limit 2. And for the integration result, we are calling this adaptive integration function. This adaptive integration function is being called in this script. So we are passing this f1. So we are passing the cos x function, the a, so the lower limit as the x1, then b as the upper limit, so it would be considered as x2, and the error limit as 1 e to the power minus 4. So here is the error limit, 1 e to the power minus 4 will be considered as this tolerance value or error limit. Okay, so if we run this code, then we can see the integration result of this cost function within 0 to 2. Okay, within 0 to 2, the value of the integration is this, and the graph looks something like this. Here is a graph. So the graph actually is the step size. We are plotting the h. If you look carefully, we are plotting h as the x on x-axis. Means the value of the h or the step size is the x-axis, and the errors are in the y-axis. So if we look at the curve, we can see if h is 0.5. So if h is a large value, then error is also a large value. The x-axis is the step size or h, segment width. Okay, the x-axis is the h, segment width, and y-axis is the error. So whenever h is 0.5, so h is a large value, the error is large as well. So whenever we have divided h by 2, like 0.5, and we divide it by 2 to 0.25, the error falls drastically. Okay, we have divided h by only 2, but the error falls very sharply, drastically. Whenever we are dividing once again, like 0.25 will get divided into 0.125, right? 0.25 by 2 will give us 0.125. So this is the 0.125 point. So for h equals 0.125, the error is this. Then it will get divided once again. So the thing that I'm trying to say is, if you divide h only by 2, the error falls very sharply. The error falls drastically. Okay, so in the first step, the error is a significant number. In the second step, the error falls very sharply. Then in the third step, it falls sharply once again. Then it continues to, the error continues to reduce very sharply. That's what I'm trying to mean by this graph. Okay, so we are dividing h only by 2, but the error gets reduced very sharply. ঠিক আছে, h কে আমরা মাত্র 2 দিয়ে ভাগ করতেছি, 2 দিয়ে ভাগ করতেছি, কিন্তু এররটা অনেক গুণ বেশি কমে যাচ্ছে একবারে। ঠিক আছে, এটাই হচ্ছে গিয়ে আমাদের এই যে অ্যাডাপটিভ ইন্টিগ্রেশন টেকনিক। এইভাবে আমরা h এর ভ্যালুটাকে চেঞ্জ করে করে আর কি সেট করতে পারি, ফিক্সড একটা ভ্যালু না দিয়ে অ্যাডাপটিভ আকারে সেট করতে পারি। So this is the adaptive integration technique, where the h is not a fixed value, rather we are setting the value of h in an adaptive manner to have a comparison in between the results, so that it satisfy our error limit or tolerance value. Okay, so that's it. I guess that's it for the adaptive integration part. I will upload the codes and the, let's stop the recording first.